Gentlemen, my name is Alex Moreno. I'm part of the Kristofer and we're part of the Berkeley Sensor and Actuation Center. Today I'll be talking to you about frequency compensated payload for wireless radio, Kristofer to be exact. And the main topic for this entire project revolves around the single chip micromode. This chip has many components. The 20 MHz Cortex M0, payload transmitter receive, 3D lighthouse optimization, which allows you to find your position in 3D space. But one thing that separates this particular chip from other ones is that it's crystal free. So that means that you don't need any passive components. You actually are able to get away from connecting power around an antenna. And we've actually shown that we can get 3 meters of range with this tiny little wire bond antenna, which is pretty nifty. But some of you might be wondering why crystal free. Why don't you use a regular radio with a crystal and just be done with whatever you're trying to do? One thing that separates crystal free radios from others is that it's low power. Typically, you save a lot of energy because you don't have to worry about your PLL or your dividers. And as a result, for this particular chip, we get 847 microwatts of transmit power consumption and RX is 1 milliwatt. So what does this give us? If we were to achieve the standard industry sleep current of 1 microamps, we currently don't have that. This is a research project, so we don't have the industry standard yet. But if we were to do that, and we were transmitting every 645 milliseconds a Bluetooth packet, we would be getting roughly 1 microcoulomb per transmission. How much it would spend, and would be spending about 0.7 microcoulomb while it's sleeping. So how does this match up to other chips? Like if TI was using, this is actually data from IO Labs. The TI chip Moreno chips, they were doing very similar thing, transmitting these beacon packets, and they were connected to a CR2032 coin cell battery. Their estimated lifespan is about 5 months, which is what IO Labs measured. But if we were to use SCUM, it would actually last 10 years, which is really good, put it lightly. So that's one reason. Another reason that's more important for us and our research group that we care about building small micro robotics is it's small and lightweight. SCUM only weighs about 4.2 milligrams, and it's a 3x2 millimeter chip. And remember, really passive, so we literally just need that chip to be able to transmit or receive data, assuming we have a good power supply. And this is valuable for the walking robot that we're working on, the flying robot. And while these are still in development, there are some use cases that we've already demonstrated that are actually quite useful with this crystal free technology. This is right here, a small sensor node. We have SCUM on the top, a flexible PCB, a battery, and we also have an antenna. And then we actually put this onto the back of a Hornet, and we use it to track its location. In Europe, there are 10 to 20% of the honeybee population is being wiped out because these Asian hornets are killing them, essentially. And so one of the solutions that we're trying to use is use this. And we were right at the edge of what this hornet could carry, 244 milligrams. Any more than that, the hornet's not going to fly. All right, so you might be wondering right now, all right, why are crystal free radios everywhere? Well, there are a bunch of challenges. Clock calibration, there are a bunch of clocks on this particular chip that we need to calibrate and know what the time reference is. And we've demonstrated different ways to get around this issue. We've done optical, we've done RF based, we've sent a packet, and the receiver uses the IF to calibrate itself. And also, another thing that this chip has is sensitivity to temperature. So we've shown that we can get around this as well. We have compensation. We can transmit from 0 degrees centigrade all the way to 100 degrees centigrade and measure temperature as a result. There's a relationship between temperature and oscillators. There's also this other really cool chip, this other cool paper that one of our collaborators published not too long ago. You can put the chip under a blow dryer that's changing its temperature 3 degrees centigrade per minute, and it can still be locked onto the actual channel, which is nice. And the last one is like, how do we actually power the system without a non-ideal power supply? In this particular situation, this is back in the Sensors 2020 conference, I presented this work where we can actually transit with the sensor on the solar only. But one of the challenges that remained for me for that particular paper was I couldn't transmit more than 10 bytes. Anything above that, the frequency not locked on, it would just not be working. And so this is what this work is all about, trying to figure out what was going on and trying to fix it. So our setup is similar to the Sensors 2020 paper. Our setup consists of a single chip micromote, which has our oscillator, has 15 bits of tunability, has LDOs, chip and clock, R chip 0, optical RX. And that's connected to ZAPI2, which is providing us with the energy that we need at 2 subs of illumination. It has a short circuit current of 560 microamps. And we also have a 100 microfarad capacitor. Quotation marks on the 100 microfarads. So one of the challenges here is that you're only providing 560 microamps, and this chip is going to draw at least 1.8 milliamps of current during its peak TX at 1.8 volts. And so what's going to happen is that the voltage is going to drop, and that's exactly what I saw when I actually measured it. During this transmission period, we have 4.5 milliseconds of transmission. We're seeing the voltage drop by 165 millivolts, and it takes about 150 milliseconds to charge it back up. So if we were continuously transmitting, we'd only be able to do it 6 times before we would be in trouble. Okay. Sorry. I was That's okay. It's okay. No, it's fine. I've been practicing all morning, so I just noticed that the room was empty, and I was like, oh, might as well. Now I'll save it for the actual talk if they'll stick around. Oh yeah, it is. Here you go. Yeah, I'm just.
What kind of battery?
It's AAA. Yeah, 2 AAA.